This is what your VRMS, your root mean square velocity, looks like. And it comes from normal move out analysis, NMO. And this is all geophysics, which we are not going to spend much time on. But the general idea is that you can have your source and your receiver, multiple receivers, and you're sending sound waves down to the formation of interest. So for this case where the source is at the same location with the receiver, the sound waves travel down, get to the reflector, and gets reflected back up, and you will record the two-way travel time. And the inverse of that is your VRMS. But for these other receivers, there is some angular offset, right? And that's what gives you what they call the seismic gatherers. Basically, this two-way travel time at different angles, right? And in normal move-out analysis, you are basically trying to estimate what this red two-way travel time will be given this time. So you are correcting for the angle. So you are moving everything back to how much time it will take if this receiver weren't here but here. And then you get your average velocity. And again, it's from the formation to the point of reflection. So what do you expect as you go down? That time will increase, right? The two-way travel time will increase as you go down, which is what you see right here. And here we're looking at the velocity. So that average velocity will increase as you go down. The outer colors are the higher values. But you see some little exceptions. In this region, the VRMS is lower than surrounding formations at the same depth. And if you look at this region, it's higher than surrounding formations at the same depth. So what do we do with this root mean square velocity? We put it into the Dix equation and use it to find the interval transit time within the formation of interest. And I gave the Dix equation in the previous module. So this is what you get using the Dix equation. So you obtain your interval or interval velocity. And similar trends, right? It's lower than surrounding formation in this region. You see this region? It's higher. The interval velocity is higher than surrounding formation at the same depth. How about here? It's lower. Very important to take note of that. Than surrounding formation at the same depth. Right? So we use a correlation equation in the textbook to obtain pore pressure from this interval velocity, and that is pore pressure equals overburden stress minus the interval velocity, which we're looking at on this slide, minus 5,000 divided by a constant b, and raise all of these to the inverse of a constant a, which is 0.62. So 1 over 0.62 is greater than 1. So what does that mean for these two regions? Let's focus on this region and this region. If if interval velocity vi increases, what happens to pore pressure? It decreases, right, because of the minus. So in these regions where VI is very high, we expect to see lower pore pressure. So we expect to see low pore pressure when we check out the next slide here. And here we expect to see high pore pressure because interval velocity is lower. So let's move on and see what we have. High pore pressure, higher than surrounding. And here, lower pore pressure, lower than surrounding formation at the same depth. So this makes sense. Another interesting point to note is, why do we report the pore pressure in pounds per gallon? Why not PSI or megapascal? We typically use reflection seismology before drilling, right? We don't have any estimate for the pore pressures, and we need to have a good idea of those values so that we don't take a kick. In order to drill the well safely, we would like to have an estimate of pore pressure. That's why we use reflection seismology to estimate pore pressure. And when we drill those wells, we're going to be thinking of mud weight in terms of what unit? Pounds per gallon, not PSI. That's why we're showing the pore pressure in pounds per gallon, which is the standard practice. Disadvantages of using compaction trends. Well, the relationship between porosity and effective stress is non-unique. And that means burial, which is an increase in loading, right? Overburden stress increases with depth. So you are loading. Porosity decreases as you go downwards, right? And here we're plotting it against effective stress. What is effective stress? Let's assume we're working with effective minimum principal stress. It's S3 minus pore pressure, right? So if we think about it in terms of what we've been looking at in module 2 and also module 1, when we're plotting your quantity of interest, say SV, pore pressure, the stresses against depth. So if this is S3 and the black is pore pressure, S3. What is effective stress? This, right? S3 minus pore pressure. So when we're looking at effective stress, you're looking at that interval, which is related to your mud window, right? That's precisely your mud window. But if pore pressure begins to build up, you're having overpressure. Should have done that with black. What happens to that mud window, which is actually effective stress? It reduces, right? And that's what you're seeing here. When you have unloading due to overpressure. So overpressure actually unloads the formation. Why? Because the pore pressure is higher, so the effective stress actually goes down. And in that case, it takes a different path, which is why we say it's non-unique. It's not unique. If it were unique, then the unloading will go back up this way, right? The curve will be the same. And why is that not the case actually in soils or in rocks? Because your grains get rearranged. If your grains were this way before, then you load, they get rearranged, right? Some of them actually break and it's more parallel and more compacted together. Now, if you decide to take off the load, the stress on it, the broken grains are not going to get back together, right? The ones that have been rearranged are not going to open up and revert back to this. That's why you have permanent deformation, which is what is called plasticity. We're going to talk about that later. And that's why the unloading path is different from the burial or loading path. If you had assumed the unloading path was same as the loading path, then you will be estimating at this value of porosity, you'll be estimating that your effective stress is this value, which is much higher than this. So if you overestimate effective stress, meaning you are overestimating this mode window, when in fact it's much smaller, then you can take a kick, right? And that's why it's important to be able to estimate these pore pressures correctly. I also give an example of what happens to effective stress when you produce. When you produce, pore pressure goes down, right? Which is your reservoir pressure. If reservoir pressure goes down, what happens to S3 or any effective stress? The effective stress is actually increased. So you actually increase the load on your reservoir as you withdraw fluids from it, which is actually interesting. So that is an example of a loading process and not an unloading process. Overpressure will be an example of an unloading process because that increases pore pressure and reduces effective stress. It's also important to note that there could be some disadvantages of using compaction trend. I already mentioned before that in sands it's not a good idea, in carbonates it's not a good idea because that normal compaction trend works well for shales. So the use of seismic data to estimate effective stress should be done with care because you could have different lithologies. You're not likely to have shale all the way from the surface to the formation of interest. And this is a field example of the loading. So you're loading this way and you're unloading this way. So the path is unique. And if you had assumed your unloading path was same as your loading path, you will be estimating effective stress, which is much smaller than, which is much bigger than the real value. And that will mean you're estimating a wider mode window when in actual fact it's much smaller.